Hello students, I am Professor Anindodar and welcome to my lecture on spectroscopy. So today is the first lecture on spectroscopy, and the spectroscopy we are studying over here is molecular spectroscopy. Molecular spectroscopy. Now, before going into some specific spectroscopy, at first we will have a generalized discussion on molecular spectroscopy. A generalized discussion on molecular spectroscopy. So, generalized discussion. First point number one. What is spectroscopy all about? What is spectroscopy all about? According to the fundamental quantum mechanics, we came to know from de Broglie wave particle duality that any matter is comprised of a dual character. Either it can behave as a particle or it can behave as a wave. So this is the inherent character of matter, and similarly there is another component of the universe, that is light. Light has also got its duality. It has got its particle nature and its wave nature. Okay. So these things are already understood to all of us. Now, as we are acquainted with the concept of de Broglie wave particle duality, we know that nature has two integral components, light and matter. Light shows duality, wave plus particle nature, and matter also exhibits duality, wave plus particle nature. So these two, light and matter, they are the independent components. They are the independent components. They are the independent components. Light and matter are independent components. Now, what if light and matter, they interact with each other? What if they interact with each other? What if they interact with each other? What if they interact with each other? And that is nothing but spectroscopy. So spectroscopy is basically the interaction between light and matter. So spectroscopy is all about the interaction between light and matter. Okay. So this is our first point, that spectroscopy is all about the interaction between light and matter. Second, what is light? What is light? In this context, light is basically an electromagnetic radiation. It's an electromagnetic radiation, EMR. Light is an electromagnetic radiation which is comprised of perpendicular electric and magnetic fields. Light is considered to be an electromagnetic radiation which is comprised of mutually orthogonal electric and magnetic fields. So these two fields, the electric and magnetic fields, they are perpendicular with respect to each other. Okay. So this is light. Next, the third one, matter. In this case, a matter is a quantum mechanical entity. It's not a classical matter. That what we are talking about in spectroscopy. In spectroscopy, we are not talking about any classical matter. In spectroscopy, we are talking about the matter which is fundamentally a quantum mechanical entity. So this matter about which we are talking about in case of spectroscopy is fundamentally a quantum mechanical entity. So this matter is fundamentally a quantum mechanical entity. It is fundamentally a quantum mechanical entity. So this matter is fundamentally a quantum mechanical entity. Okay. Now, what are the characteristic features of a quantum mechanical entity? As you are already acquainted with some quantum mechanical systems like particle in a box. You have got a number of energy levels, discrete energy levels over there. For simple harmonic oscillator, you have got a number of discrete energy levels. For rigid rotor system, you have got a number of discrete energy levels. So fundamentally, if it is a quantum mechanical entity, then it is comprised of discrete energy levels. Okay, discrete energy levels which can be degenerate or non-degenerate. So comprised of discrete energy levels, may be degenerate or non-degenerate, whatever the case may be. So this is the third point. And these two entities, light and matter, they interact with each other. These two entities, they are going to interact with each other. These two entities are going to interact with each other. These two entities are going to interact with each other. Okay. These two entities are going to interact with each other. But mind it, any light and any matter cannot interact. There must be a compatibility. So they are going to interact with each other under compatible situation. They are going to interact with each other under compatible situation. So you have to add one important clause, under compatible situation. Okay. Under compatible situation. So these are the very basic points in context to the general discussion of spectroscopy. And you have one more. You have another point, a very important point, and that point is deeply rooted into quantum mechanics. quantum mechanics. Basically, a spectroscopy is guided by this, or rather spectroscopic transitions is guided by some selection rules. So you got to have a fundamental idea of the selection rules. Let me explain it in a bit detailed manner. Selection rules. What is happening basically, so this is the initial level, this is the final level, the wave function of the final level is psi f, the wave function of the initial level is psi I, the energy of the initial level is EI, the energy of the final level is EF, this is the energy axis. And basically, this is a energy level diagram. This is the energy level diagram of any quantum mechanical system. So we have chosen a quantum mechanical system, an arbitrary quantum mechanical system, and we have plotted the energy levels. We have considered the energy levels to be non-degenerate. For the sake of simplicity, we have considered them to be non-degenerate. So you have the initial energy level marked as I, its energy is EI, and its wave function is considered to be psi I, and you have another energy level F, whose energy is EF, and its wave function is marked to be psi F. Okay. Now, an electromagnetic radiation is incident over here. Okay. So what is going to happen? See, you have some particles over here and some particles over here. The number of particles in lower energy level is greater, the number of particles in upper energy level is smaller. That is already known to us in context to Boltzmann distribution law. We are already acquainted with the fact. Now what is going to happen? This electromagnetic radiation is comprised of photons of energy h nu. Photons of energy h nu. Now, the primary condition is if there is a transition, from I to F, for a transition from I to F, this h nu must be equal to the difference between the energies of the two levels. If we want to have a transition, then the value of h nu, the value of the energy of the photon should match with the difference between these two energy levels. So what is going to happen? These photons will be absorbed by any particle. Say this particle is absorbing the photon. This particle is absorbing the photon. So photon was a particle and now it has been absorbed, completely absorbed by this particle, particle over here, So photon is the particle of light. It has been absorbed by the molecular particle over here. Okay. And what is the energy? What is the energy of the photon? H nu. So this H nu, which is equal to EF minus EI, will be transferred to this. So if the photon, this molecular particle will absorb the photon completely. And what is the energy possessed by the photon? H nu or EF minus EI. So if this molecular particle is absorbed, if this molecular particle absorbs the photon, if this molecular particle absorbs the photon completely, then the molecular particle gains an energy equal to EF minus EI. Gains an energy equal to EF minus EI. Gains an energy equal to EF minus EI. So this molecular particle is going to gain an energy equal to EF minus EI. And once it gains this amount of energy, it has already got the energy EI. Initially it has got energy EI. Initially the energy of the particle was EI. Its initial energy is equal to EI. Energy gained is equal to EF minus EI. So what should be the final energy? EI plus EF minus EI. So final energy should be equal to EI plus EF minus EI. EI will cancel out. So should be equal to EF. So the molecule will now attain the energy equal to EF. So it will move on to this state, because here the energy is EF. So this is the molecular phenomenon. This is the molecular phenomenon as how the transitions are taking place. This is the molecular phenomenon as to how the transitions are taking place. Okay. Okay. Now you recapitulate this thing a bit. I will be starting in 2 minutes time from now. Hello. So I think you all have understood this phenomenon which I have defined from the molecular point of view. So I have understood this phenomenon which I have explained from the molecular point of view. I think this is clear to you all. Okay. But still now, we don't know the concept of selection rules. That has to be clarified over here. Say, same point is being continued. This is energy. This is initial level I. So this is a final level F, and this is a final level F dash. So you have two levels. One is F and another is F dash. Okay. Say the energy of this level is EI. The energy of this level is EF. And the energy of this level is EF dash. Say the wave function of this particular level is psi I, this particular level is psi f, and this particular level is psi f dash. Now say electromagnetic radiation is coming. It is comprised of photons. Photon 1, photon 2, photon 3, and so on. Photon 1 means photon of type 1. Photon of, say, don't write it 1, say photon type 1. Say this is type 2. This is type 3, and so on. You can't have absolute monochromatic light. You can't have absolute monochromatic light. There is a range. There is a range. If it is absolutely monochromatic, then the frequency of photon is fixed. Then the frequency of photon is fixed. But you will strike with photons, not absolutely monochromatic, but it will satisfy a range of frequencies. I mean to say the photons they vary from h nu dash to h nu. Say this is the range. Okay. Now say the photon of type 1 matches with this gap, EF minus EI. And say photon of type 2 matches with this gap, say EF dash minus EI. And so on. Say there may be other levels as well. Now, my question is, which transition will take place? This one or this one? Which transition is going to take place? Will type 1 get activated or type 2 get activated or both? Which transition is going to take place? There can be other options as well, F double dash, F triple dash, and so on. So what I have done, let me repeat it once more. I have irradiated this quantum mechanical system by an electromagnetic radiation. This electromagnetic radiation is comprised of photons. This electromagnetic radiation is comprised of photons, and these photons are not absolutely monochromatic in nature. That means these photons don't have a single frequency, but it satisfies a range of frequency. It satisfies a range of frequency. It satisfies a range of frequency. A range of frequency. It satisfies a range of frequency. Why I am talking about a range? You can say you have an electromagnetic spectrum. So this is the visible range. This is the UV range. This is the IR range. This is the micro microwave range, and so on. In this direction, the frequency increases, and in this direction, the wavelength increases. Okay. Now say you are irradiating with say IR light. You are irradiating with IR light. Then IR light will not have a single frequency, but it satisfies this range of frequencies, this range is satisfied by IR light. So if you are irradiating the quantum mechanical system by IR light, then specifically you can't send a single frequency photon. On the contrary, you will be sending a photon having frequencies satisfying this particular range. And same interpretation can be made for other types as well. Same interpretation can be made for other types as well, like microwave, UV, visible, for other types as well. So this is the electromagnetic spectrum. This is the electromagnetic spectrum. This is the electromagnetic spectrum. And say you are irradiating with a visible light. That means you are not sending a single light. You can send right from violet to red. So again, what happens? Again, you can set from red to violet. That means, again, you are talking about a range. So this electromagnetic radiation is comprised of photons which has frequencies within a particular range. Say the lower limit is nu and the upper limit is nu dash. I am talking about this. This is the range. Now, photon of type 1, say it has got a frequency h nu 1. Nu 1 is falling within this range. Nu to nu dash, nu 1 is somewhere in between. And say of type 2, photon of type 2 has frequency nu 2, that is h nu 2. Nu 2 is also somewhere here. Obviously, nu 2 is greater than nu 1 because the gap corresponding to nu 2 is greater and the gap corresponding to nu 1 is smaller. So within nu and nu dash, the two arbitrary limits, we are choosing two frequencies. Nu 1 and nu 2. Now my question is whether this one will make transition or this one will make transition. Which of these two transitions will take place? It can't so happen that both the transitions are taking place. Both the transitions are taking place. There may be some exceptions, but usually you don't have both the transitions taking place. There is a selection rule. There is a selection rule to choose which of these two transitions is going to take place. I am just talking about two transitions. There can be infinite number of transitions because there can be infinite number of values of nu within nu to nu dash. So there can be infinite number of levels, and out of those infinite number of levels, there will be a choice of transition. There can be a single transition, or there can be two transitions, there can be three transitions, but all the infinite number of transitions within nu to nu dash is not going to be feasible. Now how to select the transition which is going to take place actually in nature? For that purpose, we need to understand the concept of selection rules. So selection rule, this will indicate the quantum mechanically feasible transition. The quantum mechanically feasible transition. This will indicate the quantum mechanically feasible transition. This comes from a theory known as time-dependent perturbation theory. Time-dependent perturbation theory. Time-dependent perturbation theory. But this is a class of spectroscopy. I am not going to get indulged in the details of this rigorous time-dependent perturbation theory. From time-dependent perturbation theory, one can mathematically establish a rule which will dictate the selection rules of transition. But I am not going to deduce that rule right now, because this is a class of spectroscopy. We'll be considering the results coming out of time-dependent perturbation theory, but will not go into the rigorosity of time-dependent perturbation theory right now. So the selection rule, it indicates the quantum mechanically feasible transition. The time, it is coming from time-dependent perturbation theory, and the rule that is resulting out of time-dependent perturbation theory is known as Fermi-Golden rule. Fermi-Golden rule. I am not going to deduce the Fermi-Golden rule in this context, because this is a class of spectroscopy and I am not going to get into the rigorosity of this calculation, but will be using the results of the Fermi-Golden rule. So for Fermi-Golden rule, we will develop a parameter, which is in short known as TMI. The full form is transition moment integral. So what happens here? The selection rule, it is coming from time-dependent perturbation theory. From time-dependent perturbation theory, one can establish the Fermi-Golden rule, and Fermi-Golden rule leads to a parameter which is known as TMI. The full form of TMI is transition moment integral. The full form of TMI is transition moment integral. The full form of TMI is transition moment integral. Okay. Now let's see. If a transition occurs from I to F, to say this is I and this is F. If a transition occurs from I to F, then TMI, transition moment integral, is given by mod of I square, and I is defined as bracket psi I mu cap d psi f. Okay. What is mu cap d? Mu cap d is an operator which is known as the dipole operator, dipole moment operator. It is known as the dipole moment operator. It is known as the dipole moment operator. Mu d is the dipole moment operator. Okay. It is the dipole moment operator. Now, if this I is equal to 0, then there will be no transition, and if this I is non-zero, then there will be a transition. So bracket means integration. You have to integrate psi I star mu cap d psi f over the entire space. Okay. And then you have to observe whether this I is equal to 0 or I is not equal to 0. If this I is equal to 0, then the transition is not going to take place. And if this I is non-zero, then there will be a feasible transition. Then there will be a feasible transition. Then there will be a feasible transition. Okay. Okay. So in this way, the selection rules can be developed. I'll show you some examples of selection rules, but that is too much mathematical. I'll do it once I have progressed a bit into the chapter of spectroscopy. Then I'll come back to the selection rules, and I'll be doing a few selection rules over here as well. But not now. Because that is too much mathematical and that is too much rigorous. So that is not our concern over here. Our concern is to develop the concept of spectroscopy, develop the logic behind the concept of spectroscopy. Once we have strengthened our concept, we can go into the details of these mathematical calculations. But the logic is understood. If this integral is 0, if for any transition this integral is 0, then there is no transition. And if this integral is non-zero, then there is transition. So I have to choose the non-zero integration and see what is the difference between the quantum numbers. From there, you will develop the selection rule. I mean to say, the quantum number of the initial level is I, of this final level is f, and of this final level is f dash. Say for this, I mean this one, I is not equal to 0, but for this one, I is equal to 0. This corresponds to I equal to 0, I not equal to 0, and this corresponds to I equal to 0. That means one can easily say that this transition will take place and this transition will not take place. So one can easily say that this transition from I to f is going to take place because for this I is 0, I is non-zero. And for here the value of I is 0. How can we calculate I? Very simple, you see. Here I is basically psi I mu d cap psi f. I am saying that this is non-zero. And what is the value of I here? Here the value of I is, the initial level is same, mu d cap is same, but the final level is different with wave function psi f dash. And this is 0. So naturally this transition is not going to take place and this transition is going to take place. So if this transition takes place in nature, then what is the selection rule? What is the selection rule? The selection rule is delta quantum number, change in quantum number is equal to f minus I. Change in quantum number is f minus I. That is allowed in nature, But the change in quantum number f dash minus I is not allowed in nature. So the selection rule for transition is change in quantum number should be equal to f minus I. The change in quantum number should be equal to f minus I. I think you have understood this one. Okay. Now we'll move on to a specific type of spectroscopy. We'll move on to a specific type of spectroscopy which is there in our syllabus, and that is rotational spectroscopy. Rotational spectroscopy. The very first topic of molecular spectroscopy is rotational spectroscopy. The very first topic of molecular spectroscopy is rotational spectroscopy. Now here you have got light, which is an electromagnetic radiation. That is important. And you have got matter, which is a quantum mechanical system. And they must interact. For interaction, there must be a condition of compatibility. So you have to justify the condition of compatibility. Let me repeat it once more. See, the basic requirement is the interaction between light and matter. So you have to have a light, which is an electromagnetic radiation, and you have to have a matter, which is a quantum mechanical entity. And then they must interact, and for interaction, there must be a compatible situation. So at first, let us validate these three criteria for rotational spectroscopy, then only we can move into the details. So for rotational spectroscopy, we have light, and the electromagnetic radiation is experimentally observed to be falling in the range of microwave. Okay. And the quantum mechanical system is rigid rotor model. Now you have to clarify the condition of compatibility with respect to the interaction between light and matter, that is between microwave and the rigid rotor model. So here the molecules are divided into two broad classes. Here the molecules are divided into two broad classes: polar and non-polar. For polar molecule, the dipole moment is not equal to 0. For non-polar molecule, the dipole moment is equal to 0. Okay. We'll represent a polar molecule like this, plus, minus. We are considering it to be diatomic. Initially, we are considering it to be diatomic for simplicity, and we are representing a polar molecule like this. And eventually, a non-polar molecule is represented like this, without any charge, without any charge separation. Here you have a charge separation, plus, minus. Now, at first, we will be interpreting the polar molecules. Then, we can interpret the non-polar molecules, but that will be meaningless. If we just interpret the polar molecules, we can understand what is the compatibility condition for interaction. So in order to in order to identify the compatibility condition for interaction, we are just going to interpret the polar molecule. And what is this system? What is this system? This system is a rigid rotor model. That means molecular motion is rotation. Molecular motion is rotation. Okay. So let's develop the diagram. Say we are plotting the perpendicular component of dipole moment along y-axis and angle of rotation along x-axis. Okay. Now, initially say the molecule is like this. So here, the dipole moment is acting in this direction. It is acting along x-axis. So acting along x-axis, so the perpendicular component is 0. So the perpendicular component is 0. Perpendicular component is 0 because it only has a component in this direction, so the component along this direction should be equal to 0. Okay. So this one is our first structure, but theta is equal to 0. Now you are making a rotation in this direction, and now the molecule is becoming like this. This angle is, say, pi by 2, 90 degree. Now, the dipole moment is acting in this direction. So you have got the full perpendicular component. So it comes to here. The point comes to here. Now again, we are rotating it in this direction. And the angle is becoming pi. And the dipole moment is acting in this direction. Again it is being parallel. Again it is being parallel. So the perpendicular component is being parallel to the x-axis. So the perpendicular component is being reduced to 0. This is the parallel component. This is the direction of the parallel component. And this is the direction of the perpendicular component. Okay. So it is parallel. So again it is reduced to 0. Now again you are rotating in this direction. Now this is like this. And the dipole moment is acting in this direction. And as the dipole moment acts in this direction, then what is going to happen? At this angle, 3 pi by 2. The point will come over here. The point will come over here in the negative direction. Because now the dipole moment is acting in the downward direction. It is acting in the downward direction. So we'll have the perpendicular component, but the sign will be negative because it is acting in the downward direction. Now again you are rotating it in this way, and see, you are gaining the original position. You are gaining the original position where it was 0. And this is pi. This is 2 pi. That means you have completed the cycle of 360-degree rotation. And you mark the points over here. One point is over here, one point is over here, one point is over here, another point is over here, and another point is over here. So if you join it, what are you getting? If you join this, you are getting a sinusoidal pattern. It is following the sine curve, so it is a sinusoidal pattern. It is following a sinusoidal pattern. A sinusoidal pattern which satisfies either the sine or the cosine curves. So it is following the sinusoidal pattern. And what is the pattern followed by electromagnetic radiation? The pattern followed by electromagnetic radiation is also sinusoidal in nature. The electric field is sinusoidal and magnetic field is also sinusoidal, but the two planes are orthogonal to each other. So the electric field is going to interact. We are not talking about the magnetic field. So the electric field of electromagnetic radiation is also sinusoidal in nature. We are not talking about the magnetic field now. In the interaction of magnetic field is not considered over here. In case of spectroscopy, the interaction of matter is with the electromagnetic radiation, only considering the electric field. So here the interaction will be made with the electric field of electromagnetic radiation. And we know that electric field of electromagnetic radiation is also sinusoidal in nature. So upon rotation, the matter is giving a sinusoidal pattern, and electric field of electromagnetic radiation is also sinusoidal in nature. So there will be a compatible interaction. So for polar molecules, where mu d is not equal to 0, for polar molecules I am finding that if the molecule is allowed to rotate, then it is developing a sinusoidal pattern with respect to the dipole moment. It is developing a sinusoidal pattern with respect to the dipole moment. It is creating a sinusoidal pattern with respect to the dipole moment. And the electric field of electromagnetic radiation is also following a sinusoidal pattern. So these two patterns being similar, they will be compatible. These two patterns being similar, they will be compatible. So there will be a compatible interaction. So polar molecules will satisfy the rotational spectroscopy or microwave spectroscopy. But this is not going to happen for nonpolar molecules, because for nonpolar molecules there is no change in dipole moment during rotation, because the nonpolar molecules do not possess any dipole moment. So if we are rotating a nonpolar molecule like this, you will get a straight line. It will not develop the sinusoidal pattern. It will just develop a straight line, and thereby there will be no interaction. So for rotational activity, the polar molecule will participate, but the non-polar molecule will not participate. So criteria for rotational activity is being polar. If it is polar, then the molecule will develop a sinusoidal pattern with respect to one of the components of the dipole moment. and the electric field of electromagnetic radiation is also following a sinusoidal pattern. So there will be an interaction. So there will be an interaction. So we'll have an interaction over there. And if there is interaction, there is compatibility. So the polar molecules will be compatible in terms of interaction. But what about the non-polar molecules? If you are rotating a non-polar molecule, then there will be no such sinusoidal pattern developed in terms of the dipole moment, because under any circumstance the dipole moment is 0. So you'll have a straight line which will merge with the theta axis. You'll have a straight line which will be merging with the theta axis, and thereby there is no compatibility. Okay. So this is very important, and we have developed the fundamental idea of interaction. So light, matter, and how they interact. Now we'll be moving into this matter. And we are already acquainted with the energy expressions of rigid rotor system. We are already acquainted with the energy expressions of rigid rotor system. So we'll just be moving into the expressions. So the quantum mechanical system, it is the rigid rotor system. What is the energy expression? Ej equal to j into j plus 1 h cut square by 2I. Instead of writing L, small l, I am writing the quantum number as j. By convention in spectroscopy, we use j. J is 1, 2, 3, etc. We know this. We know I is equal to mu r square. If it is a diatomic system, then this is M1, this is M2, this is R. So the value of mu or reduced mass is M1 M2 by M1 plus M2. And I is moment of inertia. Okay. So you already know these things. Now we have to express Ej in terms of nu bar j. Actually, Ej can be expressed as h nu j or hc by lambda j or hc nu bar j. Anything you wish. So, nu bar j, we will choose this by convention. Wave number will not express in terms of nu, neither will express in terms of lambda. By convention, we'll be expressing in terms of nu bar. So, nu bar j is Ej by hc. You can see it is Ej by hc. Now the value of Ej is j into j plus 1. H cut square means h square by 4 pi square. H square by 4 pi square. And you have 2 in the denominator. So it becomes 8 pi square I. Multiplied by 1 by hc. Okay. So this h is going to get cancelled out. So you are getting nu bar j to be equal to h by 8 pi square IC multiplied by j into j plus 1. Now this coefficient is denoted as capital B, which is known as the rotational constant. It is the rotational constant. But you see, B is a function of I. I means moment of inertia. And moment of inertia depends on mu, the reduced mass of the system, and R, the bond distance. That means I is a system dependent property. H is universal constant, pi is universal constant, C is universal constant. But I is a system dependent constant. So as B depends on I, that means the rotational constant is a system dependent property. It will be a constant only for a particular system, but it will vary from one system to another. Say for carbon monoxide, you will have a particular value of B. For carbon dioxide, you will have a particular value of B. For helium, for hydrogen, you will have a particular value of B. So the value of B will vary from one system to another. The value of B is going to vary from one system to another. So B is a function of I, and it is a system dependent constant. So in short, we will write nu bar j to be equal to Bj into j plus 1. So this is our final expression, and where B is h by 8 pi square IC and j varies from 0 to infinity, all the positive integers. And this is the value of B. B is equal to h by 8 pi square IC. Okay. So I have got the fundamental energy expression in terms of wave number, which we will be using in context to the rotational spectroscopy. Okay. So now we will be doing the energy level diagram. Now we will be doing the energy level diagram. For quantum mechanical system, first point done is energy expression. Energy expression. Now the second point is the energy level diagram. ELD. Energy level diagram. Our fundamental expression is nu bar j equal to Bj into j plus 1. And we know one more thing. The degeneracy. We all know that the degeneracy is given by dj equal to 2j plus 1. We all know that the degeneracy is 2j plus 1. Because the number of magnetic quantum numbers is 2 into azimuthal quantum number plus 1. So we'll have 2 into azimuthal quantum number plus 1 number of degenerate levels. So the degeneracy is 2j plus 1, that is known to us. So degeneracy is 2j plus 1. J varies from 0 to infinity. Okay. So you should keep these three factors in mind in order to construct the energy level diagram. But the energy level diagram is constructed. The energy level diagram is constructed in terms of the the wave number. So this is nu bar j. So this is 0. Now our very first level is j equal to 0. J equal to 0. What is the degeneracy of j equal to 0? If j is equal to 0, then the degeneracy is 2 into 0 plus 1, that means 1, that means non-degenerate. So you have j equal to 0. This is non-degenerate. And what is the nu bar value? The nu bar value is b into 0 plus 1, that means 0. 0. So nu bar 0 is equal to 0 and the degeneracy d0 is equal to 1, that means non-degenerate. So I've got the first one. Now the next one is j equal to 0 is done. We'll do up to j equal to 2. Now what about j equal to 1? What is the degeneracy of j equal to 1? 2 into 1 plus 1, that means 3. That means 3. So you have 3 degenerate levels. For j equal to 1, that means d1 is equal to 3. And what is the energy? What is the energy? Nu bar 1, what is the value of nu bar 1? b into 1 plus 1, that means 2b. Next, j equal to 2. For j equal to 2, we'll do up to this. You can proceed further, but we'll do up to this. Ground state, first excited state and second excited state. For j equal to 2, how many levels will you have? How many states will you have for a particular level? What will be the degeneracy? For j equal to 2, you'll have 2 into 2 plus 1. That means 5 states in level j equal to 2. 1, 2, 3, 4, 5. So for j equal to 2, d2 is 5. And what is the value of nu bar 2? See, 2 into 2 plus 1. 2 plus 1 is 3, 3 into 2 6. So it's 6b. And so on. So nu bar 2 is equal to 6b. And it will get. So now a very important observation can be made out of this. A very important observation can be made out of this. You can see what is the gap between these two levels? 2b. 0 to 2b is 2b. And what is the gap between these two levels? 2b to 6b. That means 6b minus 2b, that is 4b, etc. So what you see? You see that the energy levels are non-equispaced. The energy levels are non-equispaced. The energy levels are non-equispaced. Because the energy levels are increasing. The gap is increasing. So you can say the energy levels are non-equispaced and the gap between any two consecutive levels will increase with increase in J. I'm saying that the energy levels are non-equispaced, the energy levels are non-equispaced, and the gap between any two consecutive levels will increase with increase in J. Why? Because you see, from j equal to 0 to 1, the gap was 2b, but from j equal to 1 to j equal to 2, the gap is 4b. So with increase in j, we find that the gap is increasing. So can we give a mathematical explanation to this? Any mathematical explanation? Can any mathematical explanation be offered to this fact? Can any mathematical explanation be offered to this fact? The answer is yes, we can. You see, I'll do it here. Just find out a gap between any two arbitrary levels, arbitrary consecutive levels, j to j plus 1. Just find the gap between any two consecutive arbitrary levels. Just find the gap between any two consecutive arbitrary levels. Any two consecutive arbitrary levels. So finding the gap between any two consecutive arbitrary levels. J to j plus 1. That means it should be equal to nu bar j plus 1 minus nu bar j. Now what is nu bar j plus 1? Just substitute j plus 1 in place of j to obtain nu bar j plus 1. So you'll get b multiplied by j plus 1. You substitute j plus 1 in place of j and j plus 1 again in place of j. So j plus 1 will become j plus 2 minus bj into j plus 1. Nu bar j is bj into j plus 1. Now if you take b multiplied by j plus 1 common, b multiplied by j plus 1 common, then you are left out with j plus 2 minus j. So this jj will cancel out and thereby you are getting delta nu bar j to j plus 1 to be equal to 2b multiplied by j plus 1. So this is the expression. This is the expression, I am writing it over here. Delta nu bar j to j plus 1 in general is given by 2b multiplied by j plus 1. Now see, check it once more. So for 0 to 1 transition, this is 0 to 1 transition. This is 0, the other 0 to 1 graph, 0 to 1. So if it is 0 to 1 graph, then in place of j I am substituting 0, so it becomes 0 to 1. So in place of j you are substituting 0, so 2b multiplied by 0 plus 1, that means 2b. So you are getting 2b. Now for 1 to 2 gap, check it once more. That means 1 to 2, that means in place of j I am substituting 1. If you substitute 1 in place of j, you are getting 1 to 2. So if you substitute 1 in place of j, 1 plus 1, 2, 2 into 2, 4. So you are getting 4b. Correct. So this general expression matches with all the results that has already been deducted. So I have already deduced those expressions. You have already deduced those expressions considering specific gap. Now you are giving a generalized expression, and the generalized expression is at par with the individual results. Okay, so far so good. So far so good. Now delta nu bar j to j plus 1 is becoming 2b all multiplied by j plus 1. Now you see, this is basically a function of j. This is basically a function of j. And as it is a function of j, as the gap depends on quantum number, obviously it will be non-equispaced. Had the gap been independent of quantum number, it would have been equispaced. But as the gap depends on quantum number, so it matters whether you are making a transition from 1 to 2 or 3 to 4. It matters. That means as the gap between any two consecutive levels is a function of quantum number, it specifically means that the energy levels are ought to be non-equispaced. Okay. And what is the nature of this function? This function is an increasing function. This function is an increasing function. You can see, if you increase j, this entire thing will increase. So this is an increasing function. And as it is an increasing function, so the gap will increase, keep on increasing with increase in j. So at first you have to calculate the gap between any two consecutive levels and check whether it depends on the corresponding quantum number or not. If it does not depend on the corresponding quantum number, then the levels are equispaced. And if it depends on the quantum number, then the levels are non-equispaced. Now there can be two options. Either the gap will keep on decreasing with increase in quantum number, or the gap will keep on increasing with increase in quantum number in case of non-equispaced model. So there are two options for non-equispaced models. Either the gap will keep on decreasing with increase in quantum number, or the gap will keep on increasing with increase in quantum number. For that purpose, you have to check whether this gap, which is a function of j for non-equispaced system, is an increasing function or a decreasing function. If it is an increasing function, then the gap will keep on increasing. If it is a decreasing function, the gap will keep on decreasing. As simple as that. So we have clarified our concept of the energy level diagram for this system. Now students, we'll be moving on to the nature of the spectrum. Nature of the spectrum. Before going into the spectrum, at first we need to know the selection rules. So selection rules of transition. And criteria. So you are already acquainted with the criteria. The molecules must be polar. That is done. And what is the selection rule for transition? After undergoing time independent perturbation theory, we are getting Fermi-Dirac rule. And from Fermi-Dirac rule, we are getting the concept of transition moment integral. And from the concept of transition moment integral, one can show that delta J is equal to plus minus 1. I am not going into the mathematical details of deduction of this selection rule, delta J equal to plus minus 1 right now. I am just stating the selection rule over here, delta J equal to plus minus 1. I am just stating the result. But this can be deduced. This can be deduced by some simple steps. But now I am not going into the quantum mechanical geometry for the sake of simplicity. I am just stating the selection rule. But once I complete this chapter of spectroscopy, I'll get into the quantum mechanical detailing of these selection rules. How these selection rules are deduced from Fermi golden rule, we can establish those things. But right now, I am not going into the quantum mechanical geometry, because in that case, we'll deviate from our objective. So I am stating the selection rules right away. Delta J equal to plus minus 1. If it is plus, it means the transition is occurring from lower to the upper level. The change is positive. That means transition is occurring from lower to upper level. It represents absorption. Absorption. And if it is minus, then the change in quantum number is negative. That means transition is occurring from upper to lower level. In that case, you are having emission. Okay. So these two things have to be borne in mind. So what are the possible transitions? Possible transitions. J equal to 0 to j equal to 1. This is the first transition line. This is the first transition line. Next is j equal to 1 to j equal to 2. I am considering absorption only. So the first is j equal to 0 to j equal to 1. The change is 0 to 1, change is 1 minus 0 plus 1. So it is satisfying the selection rule. Next one, second is j equal to 1 to 2. The change is 2 minus 1, that is plus 1. Again it is satisfying the selection rule. The third one is j equal to 2 to j equal to 3. And so on. Again j equal to 2 to j equal to 3 is also satisfying this rule. So it will lead to nu bar 0 to 1. It will lead to a line from nu bar 0 to 1. It will lead to a line from nu bar 1 to 2. It will lead to a line from nu bar 2 to 3 and so on. So what should be these values? Very simple. You don't have to calculate for several times. Just remember the formula we have deduced right now. Nu bar j to j plus 1. We have already deduced it. Nu bar j to j plus 1, it is equal to 2b multiplied by j plus 1. We have already deduced this. 2b whole multiplied by j plus 1. So for 0 to 1, you just put j equal to 0. So if you put j equal to 0, you are getting 2b. We are getting 2b. So this is 2b. Now for 1 to 2, just put j equal to 1. 1 plus 1, 2. 2 into 2, 4. So it's 4b. Now for 2 to 3, just put 2. 2 plus 1, 3. 3 multiplied by 2, 6. So it becomes 6. So here you are putting j equal to 0. Here you are putting j equal to 1. You are putting j equal to 2. So how the spectrum will look like? What will be the position of the spectral lines? What will be the position of the spectral lines? So I have got nu bar 0 to 1 at 2b, nu bar 1 to 2 at 4b, nu bar 2 to 3 at 6b. So how can we get the position of spectral lines? Position of the spectral lines. In this axis, we are plotting the wave number. So we want to calculate the position of the spectral lines. So the first line is 0 to 1. It is occurring at 2b. Say this is 0. This is 0. This is the reference position. The second line from 1 to 2, it is occurring at 4b. The third line from 2 to 3, it is occurring at 6b, and so on. Okay. So these are the positions of the lines. These are the positions of the lines. Now a very pertinent observation is made from here. You see, these spectral lines, the gap between all the spectral lines are same, 2b. Although the energy levels are non-equispaced, the spectral lines are equispaced and the common spacing is 2b. 4b to 2b is 2b, 6b to 2b is 2b. So the gap between any two consecutive spectral lines is 2b. So the conclusion is, although the energy levels are non-equispaced, the spectral lines are equispaced and the common spacing between any two consecutive spectral line is 2b. What I am trying to say is, we have already established that the energy levels are non-equispaced. The energy levels are non-equispaced. But we find that the spectral lines are equispaced. That means the gap between any two consecutive spectral lines is same and the common spacing is 2b. And what is the application of this spectrum? What is the application of this spectrum? What is the application? See, from the spectrum, you just note two consecutive lines. You note the two consecutive lines. And from the spectrum, the gap between two consecutive lines is known. So from spectrum, gap between two consecutive lines is known experimentally. Experimentally, from the spectrum, you can determine the gap between any two consecutive lines. So if the gap between any two consecutive lines is known, then obviously you can determine 2b. So 2b is known. If 2b is known, you can determine the value of b. b is known. If b is known, then we know that b is equal to h by 8 pi square ic. Since all are universal constants, so if b is known, then I is known. If I is known, that means I equal to mu r square. If I is known, and for a species you know the value of mu, mu is a standard, mu is coming from standard literature, so you know the value of mu. So you can determine the value of r, that is the bond length. So you have to understand, from the spectrum, you take the spectrum, and you take the difference between any two consecutive spectral lines. You just take the difference between any two consecutive spectral lines. You just take the difference between any two consecutive spectral lines. You just note the gap between any two consecutive spectral lines. You get the gap between any two consecutive spectral lines experimentally from the spectrum. And that's what is equal to 2b. It's known to all of us. So if you know the gap, you know the value of 2b. If you know the value of 2b, you know the value of b. If you know the value of b, you know the value of h by 8 pi square IC, because b is equal to h by 8 pi square IC. Now h, pi and c are known, so you can always calculate the value of I. Now I is equal to mu r square. You already know the value of mu. Mu is a standard constant for a particular system. So if you know the value of mu, you can determine the value of radius or the bond length. So application is determination. The application is determination of bond length of a molecule. But there is a limitation. As this spectroscopy is applicable only for polar molecules, you can calculate the bond length of a polar molecule only. You can calculate the bond length of HCl, but you cannot calculate the bond length of hydrogen. So, limitation is only the bond length of polar molecules can be ascertained. We can ascertain only the bond length of the polar molecules. For non-polar molecules, we have to apply some other method. When we'll be moving into Raman spectroscopy, we'll show how to determine the bond length of polar, non-polar molecules. But right now, for pure rotational spectroscopy, we have got a limitation that the bond length of polar molecules can only be determined. Be specific with that, and that is the limitation. So we are talking about the quantum mechanical system. The quantum mechanical system first was energy expression. We have deduced that. Next, we have done the energy level diagram, and finally, we did the nature of the spectrum. Okay. Now, we will move on to intensity pattern. Actually, in a spectrum, you need to plot intensity along y-axis and nu bar j to j plus 1 or the wave number along x-axis. So from our previous discussion, we have got the x-axis. We have got the positions along the x-axis. But still now, we are unacquainted with the concept of intensity. But still now, we are unacquainted with the concept of intensity. So we have acquired the knowledge of spectrum partially. We have just come to know the position of the spectral lines. That is nu bar j to j plus 1. That is clear to all of us. We have made a quantum mechanical calculation and we have cleared this idea. But still now, we are unacquainted with the concept of intensity pattern. So now we'll be developing the concept of intensity pattern. Okay. So in intensity pattern, at first you need to know on what factor does intensity depend. Intensity, this is the fundamental concept. The fundamental concept is intensity of any spectral line, intensity of any spectral line will depend, or rather will be proportional to the population density of the level of initiation. Intensity of any spectral line will be proportional to the population density of the level of initiation. That means the level from which the transition is originating, the population of that level will be proportional to the intensity of that transition. So the intensity of a transition is directly proportional to the population density of the level from which that transition is getting initiated. Say if the transition occurs from I to F, say one transition is occurring from I to F and another transition is occurring from I dash to F. So the intensity of this transition, this intensity will be proportional to number of molecules in this level, and this intensity will be proportional to number of molecules in this level. So the intensity of a transition is directly proportional to the number of molecules of that level from which the transition initiates. So for this transition it initiates from I. So it is directly proportional to number of molecules at the ith level. And this transition initiates from I dash. So the intensity is proportional to number of molecules in the I dash level. I think you all have understood. And for that purpose, we need to apply the concept of Boltzmann distribution law. You can see Nj is equal to the degeneracy factor 2j plus 1 n by q e to the power minus ej by kbt. That's what the expression is. That's what the expression is. Okay? This is coming from Boltzmann distribution law. It has got two factors. The degeneracy factor and the Boltzmann factor. We are already acquainted with these things. Now, what is the value of N0? The reference level. J equal to 0 is our reference level. This is our reference level. So N0 should be equal to, you put 0 over here. So 2 into 0 plus 1 is 1. Acha, do one more step. N by q is there. 2j plus 1 multiplied by e to the power minus. What is the value of Ej? We know that Ej is equal to Hc nu bar j, and nu bar j is Bj into j plus 1. So Hcb j into j plus 1. What is the value of Vj? Hc nu bar j. And what is the value of nu bar j? Bj into j plus 1. So this is Bhc j into j plus 1. Just make this substitution. So it becomes e to the power minus Bhc j into j plus 1 by kBt. Now n0, just put j equal to 0. If you put j equal to 0, this becomes 1. And here again, if you put j equal to 0, this becomes 0. E to the power 0 is 1. So it's nothing but n by q. So the relative population density of the jth level, relative population density of the jth level is given by, relative population density of the jth level is given by Pj, defined as Nj by N0. We are calculating the relative population of the jth level with respect to the reference level. Reference level is j equal to 0. So it becomes Nj by N0. If we divide, then this n by q factor will cancel out, and you are left out with 2j plus 1 whole multiplied by e to the power minus Bhc j into j plus 1 by kBt. So you can see the relative population density, which is given by 2j plus 1 multiplied by e to the power minus Bhc j into j plus 1 by kBt. It has got two factors. This is factor 1 and this is factor 2. Now, you need to know the features of variation of Pj with respect to j. First one, at j equal to 0, Pj equal to P0. What is the value of P0? 1. You put j equal to 0, you will get 1. Number 2. At j tending to 0, factor 2, at j tending to 0, j square equal to 0. That means factor 2 is negligible. Factor 2 is tending to 1. Factor 2 is tending to 1. Factor 2 is tending to 1. So factor 2 is tending to 1. You have got a j square term over there. J is tending to 0. Then you have got a j square term over there. So this is negligible. So if the power of the exponential is negligible, then the exponential is tending to 1. So Pj tends to factor 1. If factor 2 is tending to 1, then Pj tends to factor 1, which is equal to 2j plus 1. It's linear, y equal to mx plus c. So you'll find a linear rise. Number 3. When j tends to infinity, very high, then factor 2 will predominate because it contains a j square term. So factor 2 will predominate. And there will be a decay. There will be a decay because you have got a negative sign over here. So what you are getting, you are plotting Pj with respect to j. At j equal to 0, it's 1. It's starting from 1. Initially showing a linear rise. Then it is followed by a decay. But you have got a limitation. You have got a limitation. You have got a limitation. This plot cannot be continuous because j is not continuous. So this plot is not continuous. Basically, j is not continuous. You don't have continuous value of j. You have j equal to 0. J equal to 0. Then you have j equal to 1. Then you have j equal to 2 and so on. So you don't have continuous value of j. You don't have continuous value of j. So this plot is not continuous. It's a quasi-continuous plot. This plot is not continuous. This plot is not actually continuous. This plot is not actually continuous because j is not a continuous variable. This plot is not actually continuous. This plot is not actually continuous. This plot is not actually continuous since j is not a continuous variable. Since j is not a continuous variable. As j is not a continuous variable, this plot can never be continuous. This plot can never be continuous. But for the sake of mathematical simplicity, we are considering it to be a continuous plot. For the sake of mathematical simplicity, we are considering it to be a continuous plot. So from here, we need to calculate this maxima. This is j max. At j equal to j max, the relative population density gets maximized. So the fourth point is, at j equal to j max, pj equal to pj max, that means the first order derivative is 0. But we are differentiating this function. That means we are forcefully considering the function to be continuous. Although the function is not actually continuous, we are forcefully considering the function to be continuous in order to calculate j max. So this is a forceful consideration. This is a forceful consideration. Okay. So you have got nu over j, you have got pj to be equal to 2j plus 1 whole multiplied by e to the power minus bhc j into j plus 1 divided by kbt. Now we are differentiating it with respect to j, dpj, dj. So we are following the UV method. At first we are differentiating 2j plus 1. So it becomes 2 into e to the power minus bhc j into j plus 1 divided by kbt. Plus 2j plus 1 is there. Then you are differentiating this one. So if you are differentiating this one, then the exponential term will be repeated. e to the power BHC j into j plus 1 divided by kBt. Now you have to differentiate the exponential term, the term within the exponential. So you're getting minus BHC by kBt, which is a constant, and you are differentiating j into j plus 1. J into j plus 1 is nothing but j square plus j. So if you differentiate j square plus j, you are getting 2j plus 1. So you take e to the power minus BHC by e to the power minus BHC j into j plus 1 by kBt common from both this. Then you have got 2 minus sign. See, you have 2j plus 1 twice, so it becomes 2j plus 1 whole square. And you have got, let us write the constant at first. BHC by kBt multiplied by 2j plus 1 whole square. But that's it. Now at j equal to j max, this entire term is 0. And we know that j max is not equal to infinity. So this term is non-zero. That means this term must be 0. So at j equal to j max, this term is 0. That means BHC by kBt whole multiplied by 2j plus 1 whole square should be equal to 2. So at j equal to j max, we know that dpj dj is 0, dpj dj is 0, and we also know that j max is not equal to infinity, so this term is non-zero. Thereby, we'll have BHC by kBt whole multiplied by j max plus 1 whole square to be equal to 2. So from here, one can evaluate j max to be equal to 2 kBt by BHC, 2 kBt by BHC square root of 2 kBt by BHC minus 1. Sorry, 2j max plus 1. So 1 divided by 2. So from here you are getting this. It could have 2 roots, but j max can never be negative. That's why we are using only this root. Since j max can never be negative, we know that j is not negative, so j max can never be negative, so we are using this root. So eventually you'll see that j max is equal to, if you divide by 2, then it becomes root over of kBt by 2 BHC minus half. So this is the expression of j max. This is the expression of j max. This is the expression of j max. So if for the given system, if for the given system say j max equal to 3, then what will be the spectrum looking like? say Jmax equal to 3. A spectrum is basically a plot of intensity along this direction and nu bar j to j plus 1 along this direction. So which line will have highest intensity? The line where Jmax is the initial level, that means Jmax to Jmax plus 1 will have highest intensity. The line with Jmax to Jmax plus 1 will have highest intensity because Jmax has highest population. As Jmax has highest population, so the line with Jmax to Jmax plus 1 has highest intensity. So it's known that highest intensity will occur for Jmax to Jmax plus 1 transition. So 3 to 4 transition will have highest intensity. This is 2 to 3. This is 1 to 2. This is 0 to 1. Again after 3 to 4, there will be decrease. 4 to 5. 5 to 6, and so on. And we all know that the gap will remain the same. Okay. So this is what the spectrum will look like. This will be the nature of the spectrum. This will be the nature of the spectrum. Okay. So that's all for now, for today's class. And we have covered a bit of rotational spectroscopy, and we have done a general discussion on spectroscopy. So in the next class, we'll be proceeding with the rotational spectroscopy as usual. So thank you all. Bye bye for now.